What do you hear right now? The hum of a fan. Traffic outside. Maybe rain. The human brain is wired to constantly search for sound because for millions of years of evolution, total silence usually meant something dangerous was coming. So what does space, where there is nothing at all, actually sound like? The familiar answer: complete silence. A vacuum has no molecules, no medium for sound to travel through. That much is true. But stopping there means missing the far more interesting part. The universe is full of vibrations: plasma waves, radio waves, X-rays, electromagnetic waves, gravitational waves. Not sound in the conventional sense, but all of them carry data. When scientists translate that data into audio signals, a technique called data sonification, what they hear sometimes keeps people up at night. A comet hurtling through the solar system, producing something that sounds remarkably like a living creature breathing. A black hole 240 million light years away, rumbling at frequencies so low that no human body could ever perceive them without the intervention of machines. And from a collision that happened before Earth even existed, the universe left behind an echo that took humanity an entire century to learn how to hear. What do those sounds actually sound like, and what do they tell us about the universe we live in? In space, no one can hear you scream. That line appeared on the poster for the 1979 film Alien, and has since become one of the most famous sentences in cinema history. Physically speaking, it is completely correct. Sound waves need a physical medium to travel through. The vocal cords vibrate, pushing air molecules into each other in a chain, generating pressure waves that travel to the listener's ears. A vacuum has no molecules to push, so sound, in the conventional sense, genuinely does not exist out there. The thing is, between planets, between stars, even between galaxies, the universe is never truly completely empty. Thin plasma, dust, gas, and countless forms of radiation permeate every corner of space. Plasma in a planet's magnetosphere generates electromagnetic waves. Pulsars emit radio waves with the regularity of atomic clocks. Black holes blast X-rays from the superheated gas disk, swirling around them at millions of degrees. And then there is something stranger still: gravitational waves, vibrations that require no medium at all because they are the stretching and compressing of space-time itself. All of those vibrations carry information. Data sonification is the technique of translating that information into a language human ears can receive. Not by fabricating sounds for dramatic effect, but by mapping real data onto real frequencies. Think about how scientists use charts and heat maps to see hidden patterns in massive datasets. Sonification does the same thing, but through the ears. And ears are sometimes sharper than people give them credit for. In a complex dataset, the eye might miss a subtle oscillation, an irregular repeating pattern, a frequency that does not belong to the general model. The ear tends not to, because the human brain is wired to detect anomalies in sound faster than any other sense. And this is not just about putting on a good show for audiences. Scientists genuinely use sonification as an analytical tool, because in a vast dataset drawn from solar wind, from plasma around black holes, from gravitational waves after a collision, the ear sometimes catches what the eye misses: a repeating anomaly, an off-key oscillation, a frequency that falls outside the expected pattern. Those discoveries sometimes completely change how we understand a phenomenon. The first case that proves exactly that came from one of the last places anyone would have expected: the icy rings of Saturn. From a distance, they look solid, rigid, almost perfect. When Galileo first glimpsed them through his primitive telescope in 1610, he could only describe Saturn as a planet that appeared to have ears. Get closer, and everything starts getting complicated in ways nobody anticipated. Saturn's rings are not a solid disk. They are billions of fragments of rock and ice, ranging from specks of dust smaller than a grain of sand to boulders the size of houses, all orbiting the planet in a chaotic but orderly dance. Many of those particles carry electrical charges, constantly ionized by solar radiation, turning the rings into an extraordinarily complex electromagnetic environment. Saturn has an enormous magnetosphere, a region of space dominated by the planet's magnetic field and filled with charged plasma. When electrically charged particles in the rings interact with the plasma in the magnetosphere, they come under the influence of the Lorentz force, which causes charged particles to spiral along magnetic field lines like a spinning top. That movement generates oscillations in the plasma, spreading outward like waves across an invisible lake, entirely beyond the range of human perception. And this does not only happen at the rings. Similar interactions are constantly playing out between Saturn and every moon in its orbit, each connection forming its own separate circuit of vibration. NASA launched the Cassini spacecraft on the 15th of October 1997. It took nearly 7 years to reach Saturn, covering 3.5 billion kilometers by borrowing gravitational momentum from Venus, Earth, and Jupiter along the way. Cassini carried an instrument called the Radio and Plasma Wave Science Instrument, or RPWS, designed specifically to record electromagnetic waves and plasma oscillations in Saturn's environment. The instrument was sensitive enough to detect lightning in Saturn's atmosphere from thousands of kilometers away. In the thinnest of Saturn's rings, there are dust particles only around 200 nanometers across, roughly the size of a virus. When those microscopic particles struck Cassini's sensors, they created tiny pockets of plasma, like miniature lightning bolts, flaring and fading in an instant. Each collision produced a signal, thousands of signals every second. When the RPWS team at the University of Iowa converted those signals into sound, what came out of the speakers resembled rain hammering against a metal surface, hissing, crackling, threaded through with strange whooshing sounds unlike anything familiar on Earth. The kind of audio that triggers an immediate, visceral reaction. I was not supposed to hear this. Then in September 2017, during the final orbits of the grand finale mission, Cassini recorded for the first time the direct movement of plasma waves travelling along magnetic field lines connecting Saturn to its moon Enceladus, hundreds of thousands of kilometers apart. Nobody had anticipated that connection at that scale and intensity. The magnetic field lines between the two bodies were acting like a massive electrical circuit, with energy flowing back and forth continuously. Enceladus, the small moon that shoots water, plumes out from beneath its surface into space, turned out to be a natural generator that never switches off, quietly powering Saturn's entire magnetic system for billions of years without. That recording was made on the 2nd of September 2017. 2 weeks later, Cassini was deliberately steered into Saturn's atmosphere and destroyed to eliminate any risk of the spacecraft losing control and contaminating moons like Enceladus that might harbour life. Nearly 20 years in space, and the last recording it sent home was the quiet exchange between a planet and its moon, as though Cassini somehow knew it was about to end and chose to listen one last time before it did. And during that same period, in another corner of the solar system entirely, a different spacecraft was listening to a completely different object, smaller, darker, and producing something that sounded disturbingly close to the breathing of a living creature. Comet 67P, Churyumov-Gerasimenko. A long and difficult name, but this is one of the most thoroughly studied objects in the history of space science. 67P orbits the Sun in the outer solar system, taking roughly 6.5 years per orbit on a path between Earth and Jupiter. Scientists believe objects like 67P are fossils of the solar system itself, primitive material left over from more than 4 billion years ago when the planets had not yet formed and everything was still a swirling cloud of gas and dust collapsing inward. In 2004, the European Space Agency, ESA, launched the Rosetta spacecraft to chase down 67P. That took 10 years. Rosetta had to fly past 4 other planets to borrow enough gravitational momentum, and at one point had to shut down all its systems and drift through space for 31 months just to conserve energy. In August 2014, Rosetta finally caught up with 67P and entered orbit around the comet. Then on the 12th of November 2014, the Philae lander detached and touched down on the surface, the first time in human history that a man-made object had landed on a comet. Rosetta carried several plasma measurement instruments, including a Langmuir probe to measure electron density and plasma oscillations in the environment surrounding the comet, and a magnetometer to detect magnetic field fluctuations caused by plasma waves as solar wind struck the coma and tail of 67P. Together, those two data sources produced a comprehensive picture of the plasma dynamics around the comet at a level of detail that had never been achieved before. When that data was translated into sound, what came back was a strange combination. A rhythmic clicking representing periodic oscillations in plasma density as solar wind swept continuously through the comet's coma, layered beneath a long, sustained hum, like the groan of something enduring relentless pressure from outside. Many people hearing it for the first time compared it to sounds creatures make in horror films, something organic and irregular that triggered survival instincts, even as the rational mind understood this was nothing more than magnetic field data. What particularly caught scientists' attention was that 67P's sound was distinctly different from any previously measured comet, including the famous Halley's Comet. That suggested 67P had its own unique physical characteristics, that each comet carries a distinct plasma structure around it, something close to an electromagnetic fingerprint that cannot be mistaken for anything else. An object that formed 4 billion years ago has its own voice. If that is already strange enough, what waits at the next stop is stranger still, in a completely different way. Not a whisper, not a groan, a roar, from something with a mass 800 million times that of the Sun, sitting 240 million light years away. Take a moment and think about what that number actually means. Light travels faster than anything in the universe, 300,000 kilometers every second. Yet light leaving the Perseus galaxy cluster takes 240 million years to reach our eyes. When that light left Perseus, Earth had no dinosaurs, no mammals. Life on this planet was nothing more than simple marine organisms feeling their way through shallow oceans. And at the center of that galaxy cluster, through all of that time, a black hole has been roaring at a frequency no living thing in the universe could ever hear. The Perseus cluster is one of the largest structures in the observable universe, stretching across tens of millions of light years and containing thousands of galaxies, all held together by shared gravity within an enormous cloud of gas and plasma known as the intracluster medium, the space between galaxies. The gas in that environment is so hot it only glows at X-ray wavelengths, temperatures of tens of millions of degrees Kelvin, hotter than the cores of most stars. At the center of the Perseus cluster sits the galaxy NGC 1275, and at the center of NGC 1275 sits a supermassive black hole estimated at around 800 million times the mass of the Sunday. Black holes of this type continuously consume gas from their surroundings, driving matter into an accretion disk that spirals around them at terrifying speeds, reaching temperatures of millions of Kelvin, and, in the process, blasting out X-rays and ultraviolet radiation with enormous energy. In 2003, NASA's Chandra X-ray Observatory, a space telescope dedicated entirely to X-ray observation, recorded detailed data on the Perseus cluster. Chandra does not see in ordinary light. It captures individual X-ray photons and reconstructs temperature and density maps of the hot gas surrounding the black hole at unprecedented resolution. In that data, scientists discovered pressure waves radiating outward from the black hole, pushing into the surrounding gas, the way sound waves push through air, with an oscillation period of around 10 million years per cycle. In 2022, scientists returned to the Chandra data and for the first time converted those pressure waves into sound. What they found was a musical note, B flat, 57 octaves below middle C on a piano, one of the lowest frequency sounds ever detected anywhere in the universe. To bring it into a range human ears could actually hear, NASA had to raise the frequency by 144 to 288 quadrillion times, a number that puts virtually every human intuition about scale out of reach. The most common first reaction upon hearing it was not awe, it was unease. The sound is deep, heavy, and sustained, Like the rumble of something breathing at a frequency the body registers before the mind has time to process it. The unsettling quality does not come from sudden shock or surprise. It comes from the slow, creeping recognition that whatever is making that sound is larger than anything the human mind is actually equipped to imagine. And the scientific significance of that sound goes far beyond making an impression. The acoustic waves radiating out from the black hole push energy into the intracluster medium, the vast, hot gas environment surrounding thousands of galaxies within the Perseus cluster. That energy may be helping maintain the temperature of that environment, preventing the gas from cooling down and collapsing into new stars. In other words, the roar of the black hole at the heart of the Perseus cluster may be actively regulating the rate of star formation across the entire cluster, shaping the evolution of thousands of galaxies simultaneously through a mechanism we have only just begun to understand. And if the roar of a single black hole can carry that much information about the evolution of an entire galaxy cluster, the natural next question becomes, what else is encoded in the vibrations of the universe that we have not yet learned to read? The answer begins with a prediction written down more than a century ago. In 1916, Albert Einstein published his general theory of relativity, one of the greatest intellectual achievements in the history of science. In it, he predicted that massive objects, when accelerating or colliding, would generate disturbances that propagate through the fabric of space-time, ripples spreading through the very structure of space and time itself, much like a stone thrown into a pond sends rings spreading across the surface. He called them gravitational waves, and in that same paper he added that he doubted humanity would ever be able to detect them. The amplitude would be too small, the sources too distant, and human technology, however advanced it became, would probably never be sensitive enough. More than a century later, humanity proved him wrong. To detect gravitational waves, scientists built a class of instrument unlike any telescope ever constructed. Instead of lenses or mirrors, they used lasers. At LIGO facilities in the United States, Virgo in Europe, and Kagra in Japan, laser beams are fired down 2 vacuum tunnels several kilometers long, positioned at right angles to each other. These 3 facilities operate as a network, working together to confirm signals, determine their direction of origin, and pinpoint their source in the sky. Under normal conditions, the laser beams traveling in both directions take exactly the same amount of time to complete their journey. When a gravitational wave passes through, it stretches space-time in one direction and compresses it in the other, creating an infinitesimally small change in the path length of the laser on the order of 1/10,000th the diameter of a proton. When the laser path stretches or compresses, the signal shifts in frequency, much like a tighter guitar string produces a higher note. Higher frequency maps to higher pitch, and through that process, gravitational waves can be converted into sound the human ear can hear. On the 14th of September 2015, LIGO detected its first signal, an event designated GW150914. 2 black holes, one at 36 solar masses and one at 29, had been spiraling around each other for billions of years, their orbit tightening with every loop as they bled energy away in the form of gravitational waves. Then, approximately 1.3 billion years ago, they merged in a fraction of a second, releasing energy equivalent to 3 times the mass of the Sun, entirely as gravitational radiation. In that brief moment, the collision released more power than the combined light output of every star in the observable universe. When that signal was translated into sound, what people heard was a chirp, a short rising tone that cuts off abruptly, the entire thing lasting less than a second. Compressed into that fraction of a second was the entire billion-year journey of 2 black holes falling toward each other. Every collision has its own sonic character. 2 lighter black holes spiraling in slowly produce a longer chirp, with frequency climbing gradually. 2 more massive black holes merging fast and violently produce a short, heavy chirp where the frequency jumps in an instant. Physicists can read from the shape of that chirp the mass of each black hole, the distance to the source, even their spin rates before impact. This is direct evidence for one of the greatest predictions in the history of general relativity, and a reminder that humanity has found a way to observe the universe through something deeper than light, through the vibrations of the very structure from which the universe itself is woven. And it all started with a question that seems almost too simple. What does space sound like? We have traced 4 answers. The electromagnetic whisper between Saturn and Enceladus, the final recording of a spacecraft that spent nearly 20 years in the void, the strange breathing of a 4 billion-year-old comet drifting alone through the solar system, the deep roar of a black hole shaping the evolution of thousands of galaxies through a mechanism we have only just started to grasp, and a chirp lasting less than a second, the acoustic fingerprint of 2 black holes that collided before Earth existed, leaving a tiny ripple in the fabric of space-time that humanity spent an entire century learning to hear. Calling space silent is too simple an answer. The universe is not mute. It vibrates at frequencies the human body was simply never built to perceive directly. But when we build the right tools, ask the right questions, and stay patient enough to listen, what echoes back is not emptiness. It is a symphony that has been playing since long before there were any ears in the universe to hear it. The question was never whether the universe has anything to say. The question is whether we are finally ready to listen.